Hello friends. Now we continue with the ionic equilibrium in chemistry. That is in part 2. Okay. Means we start ionic equilibria part 2. Now first we see what is the type of salt here. Now see, you have a salt that is NaCl or CuSO4. Now this salt is formed due to the reaction between your acid and base, then you get a salt and water. Now first we see what is the type. So there are 4 types of salt. So first salt that is derived from strong acid and strong base. Now see this example, NaCl. NaCl is formed due to the reaction between NaOH and your HCl. See, NaOH is a strong base and HCl is a strong acid. As we know, that is why this is strong acid or strong base, because they dissociate completely in water. Now next example is Na2SO4. Now Na2SO4 is formed due to NaOH and H2SO4. Similarly, NaNO3 is formed due to NaOH and HNO3. KCl is formed due to KOH and HCl. And KNO3 is formed due to KOH and HNO3. Now, you must know what is the example of strong acid and strong base. Say strong base example is KOH, NaOH, and strong acid example is HCl, H2SO4 and HNO3. Now, next salt, that is a second type, which is derived from strong acid and weak base. As you know, weak base example is NH4OH, CuOH twice. These are the example for weak base. Okay. Now, when you treat NH4OH with HCl, you get NH4Cl. So this is the example of your strong acid and weak base. Now next is CuSO4. So CuSO4 is formed due to the CuOH twice and H2SO4. Now in this case H2SO4 is a strong acid and CuOH twice is your weak base. Next is NH4NO3. In this case also the salt is formed due to NH4OH and HNO3. Next is CuCl2. So CuCl2 is formed due to CuOH twice and HCl. So HCl is your strong acid and CuOH twice is your weak base. Now third example means third type of salt, that is a salt derived from weak acid and strong base. So as you know, weak acid means what? That is your acetic acid, then your carbonic acid. These are the example of your weak acid. So when this weak acid reacted with your strong base, then you get the salt that is which is derived from weak acid and strong base. So example is CH3COONA. Now in this case CH3COONA means what? It is derived from acetic acid, that is CH3COOH and NaOH. Okay. Next example is your KCN. Okay. So in KCN is formed due to KOH and HCl. The next example is Na2CO3. So in this case, your weak acid is H2CO3 and strong base is NaOH. React and you get Na2CO3 salt from that. Now last type of salt is nothing but which is derived from weak acid and weak base. So example is what? Weak acid means what? That is your acetic acid. Then your HCl, that is your weak acids. And weak bases are what? NH4OH, then COOH twice. So example, see the example, that is CH3COONH4. Now in this case, this salt is formed due to the reaction between acetic acid, that is CH3COOH plus NH4OH. Okay. Now next is NH4Cl. So in this case, your salt is formed due to the reaction between NH4OH and HCl. Now our next slide is on basis of, that is nothing but your hydrolysis of salt. But first we see the type of salt. Now next we see what is the concept of hydrolysis. Okay. Now see, when any salt dissolve in a water, so what happen? It dissociates completely into its constituent ion, and the solvent molecule dissociates slightly as. Then see, as concept of hydrolysis means what? You take a salt and you add that salt in a water. So what happen? Your salt is made up of cation and anion. So it completely dissociates into your solvent. That is nothing but in this case water. So now, but at the same time your solvent, that is water, is also dissociate as H3O plus and OH minus. Now see, your water molecule is also dissociated into two ions, that is H3O plus cation and OH minus anion. Now in case of pure water, the concentration of both the species, that is your H3O plus as well as OH minus ion, are equal. So that's why they are neutral, means pure water is a neutral. Okay. Now if your ion of a salt, means salt is made up of ion, that is cation and anion, if they doesn't react with the water molecule, so now what happen? The concentration of your dissociation of a concentration of the ion which is formed due to the water dissociation, that is hydronium ion and hydroxyl ion, so remain equal, and the solution is neutral. It's clear? So whenever your ion of salt does not interact with your ion of a water, that is hydronium ion and hydroxyl ion, so their concentration remain equal and the solution is neutral. Now if the ion, that is one or more of the salt ion, react with the water, so now what happens? The concentration of the hydronium ion and hydroxyl ion is disturbed. Means whenever your salt doesn't interact with your water molecule, so at that time concentration of hydronium ion and OH minus ion remain undisturbed and your solution remain as a neutral. But whenever the ion of a solution interact with your water ion, that is hydronium ion and OH minus ion, so at that time their concentration disturbed and the solution, you said, it may be acidic, it may be basic. Okay. Now, so how will you define the hydrolysis of salt? So hydrolysis of salt is defined as the reaction in which cation or anion or both the ion of a salt, means your salt have both the ion, that is cation also and anion also. So in hydrolysis, at one time maybe cation interact, or in some cases anion interact, or in some cases both interact with your ion of a water to produce acidity or alkalinity or sometimes even neutrality. So that is a very important definition. What is the definition? Hydrolysis of a salt is defined as the reaction in which cation or anion or both the ion of a salt react with the ion of a water to produce acidity or alkalinity, or sometimes even neutrality. So this is nothing but your hydrolysis of salt, means concept of hydrolysis. In hydrolysis of salt, first we see the type of salt, second we see the concept of hydrolysis. Now next we see that is all our four types of salt. So how it form acidic solution, basic solution or neutral solution, that we have to determine. Means after the hydrolysis of these four type of salt, your solution now behave as a what? Acidic, basic, neutral or something else. Okay. Now see. The first one, that is salt of a strong acid and strong base. Now for this we take example of NaCl. Now see, NaCl is made up of strong acid, that is HCl, and strong base, that is NaOH. So when this salt we dissolve in a water, so now the salt dissociate into two ions, that is Na plus and Cl minus. Okay. Now what happened? But the ion which is formed, that is Na plus and Cl minus, have no tendency to react with water. Okay. Means what? Means Na and Cl does not have a tendency to react with water. And this is because the possible product NaOH and HCl of such a reaction are strong electrolyte and dissociate completely in aqueous solution. Means as soon as HCl and NaOH form in the reaction, so once again they dissociate into Na plus and Cl minus ion. Means there is no tendency for Na and Cl minus ion to interact with the water molecule. So if your reaction, that is Na plus Cl minus, react with the ions of water, you get a HCl and NaOH, but that HCl and NaOH once again dissociate into Na plus and Cl minus. Now see, strong acid, that is HCl and NaOH, this is your possible product. But that product, once again, they are a strong electrolyte, so that's why they completely dissociate in aqueous solution. Okay, so that's why your reactant and product are the same. If you see the reactant and product, so they are the same. So this implies that neither cation nor anion of a salt react with the water, or there is a no hydrolysis. So this is, in this way, your equality between hydronium ion and OH minus ion produced by ionization of water is not disturbed, and solution is a neutral. So it may be concluded that salt of a strong acid and strong base does not undergo hydrolysis. So this is clear. One more time I have to explain this. This is because the salt of strong acid and strong base, when they undergo hydrolysis in water, so what exactly happen? Your salt, that is NaCl, when dissolved in a water, you get Na plus and Cl minus ion. So that Na plus and Cl minus ion, if react with H2O, so you get NaOH and HCl as a your possible product. But NaOH and HCl is a strong electrolyte, so they once again dissociate into its ion. And that's why your Na plus and Cl minus ion does not interact with your hydronium ion or OH minus ion of the water molecule. So that's why they maintain the electrical neutrality. and your solution become neutral. So it may be conclude that salt of strong acid and strong base does not undergo hydrolysis. Now we see our next type of salt, that is salt of strong acid and weak base. So for this we take an example of copper sulfate. Now see, copper sulfate is a salt which is derived from strong acid, that is H2SO4, and weak base, that is copper hydroxide. Okay, as soon as you dissolve the salt, that is copper sulfate, in a water, so now which two types of ion you get from that? That is Cu2 plus and SO4 2 minus. Okay, now in this case SO4 2 minus is coming from strong acid, so that's why they doesn't have any tendency to react with the water molecule. Okay, because SO4 once again react with H2, you get H2SO4. So that is a strong electrolyte, so it's once again dissociate into its constituent ion. But in this case there is another cation, means another ion, that is nothing but your Cu2 plus cation, that react with OH minus ion of your water molecule and form unionized CuOH twice. Now see, in this case Cu react with the water, you get CuOH twice. So this CuOH twice is a weak electrolyte, so you doesn't get once again the Cu2 plus from that. Okay, so that's why whenever Cu react with the water, you get CuOH twice and H3O plus, that is hydronium ion. So due to the presence of excess of hydronium ion, the resulting solution of CuSO4 become acidic and turn blue litmus red. Means see, as your CuSO4 is made up of CuOH twice and H2SO4, so when CuSO4 dissolve in a water, you get Cu2 plus and SO4 2 minus. So in that SO4 2 minus anion doesn't have any tendency to react with water, but Cu react with the water and you get CuOH twice and hydronium ion. So due to the hydronium ion, what happened? Your CuSO4 solution become acidic and turn blue litmus paper red. Now in this case, formation of a sparingly soluble CuOH twice by hydrolysis make the aqueous solution of copper sulfate turbid. So in this case, when you dissolve copper sulfate in water, so you get a sparingly soluble copper hydroxide from that. Okay, and if H2SO4, that is H3O plus ion, are added, the hydronium ion equilibrium shift to the left. Means what happen? As copper sulfate in water, you get a turbidity. Okay, and if you added H2SO4 in that, so now your equilibrium shift to the left. Matlab, in this case, CuOH twice, which is formed and which gives the turbidity to the solution, now dissolve in that excess of H2SO4 and you get a clear solution. So in this case, when you have a clear solution of H2SO4, means the addition of H2SO4 will be required in that. Okay, so what is the meaning of that? In this case, you form a sparingly soluble CuOH twice, and which is formed by hydrolysis make the aqueous solution copper sulfate turbid. If H2SO4, means if you add H2SO4 in that, so what happen? Your hydrolytic equilibrium shift to the left. Okay, and the turbidity of copper hydroxide dissolve to get a clear solution. So to get a clear solution of copper sulfate, what is the requirement? We have to add excess of, or we have to add extra sulfuric acid in that. Now we see the next type of salt, that is salt of weak acid and strong base. In case of salt of strong acid and weak base, we get a acidic solution. Now we have to see in salt of weak acid and strong base, what is the nature of our solution. Now for this, we take an example of sodium acetate. Now in this case, sodium acetate is a salt of what? Weak acid, that is acetic acid, and strong base, that is NaOH. Okay, when sodium acetate is dissolved in a water, so now what we get? Na plus and CH3COO minus. Now the water molecule also dissociate into H3O plus and OH minus ion. So solution of a sodium acetate contain Na plus, H3O plus, CH3CO minus and OH minus ion. So in that case, Na plus ion doesn't have a tendency to react with OH minus ion of a water. Okay, because you get a possible product, that is NaOH, which is a strong electrolyte, so it's once again dissociated into Na plus and OH minus ion. But at the same time, CH3CO minus anion of a salt have a tendency to react with H3O plus ion from water. So now your product will be CH3CO minus O minus plus H2O. You get CH3COOH plus OH minus, means you get acetic acid and OH minus ion. So now what happened in when you dissolve sodium acetate in water, so what is your possible product? Acetic acid, Na plus and OH minus ion. So as a result, in this case, you get an excess of OH minus ion, and that's why your solution become basic. Okay, so that's why sodium acetate, when dissolved in a water, you get a basic solution from that. Okay, so now see what we do in this case. In this salt, if you take a sodium acetate, dissolve in a water, so your solution become basic in nature. So now as far we study three salt, that is first salt is made up of strong acid and strong base, so in that case your solution become neutral. And when we study the salt of strong acid and weak base, so in that case our solution is acidic in nature. And when we study the salt of weak acid and strong base, so at that time our solution is basic in nature. So in this way we complete our three salts. Now last salt, that is nothing but salt of a weak acid and weak base. Now for this we take example of salt of BF. Means what? In this case BF is a salt which is made from weak acid, that is HA, and weak base, that is BOH. Okay, and that is dissolved in a water. So now what is the product, or what is the ions they given to you, that we have to see. So see, in this case we take a general example for salt of a weak acid and weak base, that is nothing but Ba. Okay, and in that case your Ba is made up of weak acid, that is HA, and weak base, that is BOH. Okay, and BA, when dissolved in a water, you get B plus and A minus. Okay, now in this case, when the hydrolysis reaction involves the interaction of both the ion with the of the salt with the water, so B plus and A minus both react with the H2O. So now what is your product? In this case we get a BOH and HA is a both the compound are nothing but we get a weak base and weak acid from that. Okay, so now in this case you have to decide which solution is acidic, basic or neutral. So how will you decide? It will be decided on the basis of your relative strength of a weak base and weak acid formed in the hydrolysis. Now see, in this case there is a formation of a weak acid as well as there is a formation of a weak base. Okay, so if your Ka is greater than Kb, means your dissociation constant for acid is greater than your dissociation constant of a base, so at that time your solution will be acidic in nature. Now second part is what? If your dissociation constant of acid is less than dissociation constant of base, then your solution will be basic in nature. And third one, if your dissociation constant of acid and base both are equal, then your solution will be neutral. See, for the salt of weak acid and weak base, if you have to decide your nature of your nature of your solution, so at that time you have to consider these 3 points. That is nothing but the acid, weak acid and weak base which is formed in a solution. So out of these two compounds, which one having more dissociation constant, that will decide your solution nature. Means the dissociation constant of acid will be more, then your solution will be acidic. If dissociation constant of base will be more, then your solution will be basic. And if your dissociation constant of both acid and base are equal, then the solution will be neutral. So we have to see one by one. That is, first we take the first case, that your dissociation constant of weak acid, dissociation constant of your weak acid is greater than dissociation constant of weak base. So now for this we take example of NH4F. Okay, and it is a salt of what? Weak acid, that is HF. So HF have a Ka value that is 7.2 into 10 raised to minus 4, and weak base, that is NH4OH, which have a Kb value that is 1.8 into 10 raised to minus 5. Now in this case your Ka will be greater than Kb, as you can see from the values. Now if you dissolve the NH4F salt in a water, so what is your product? So NH4 plus F minus plus H2O gives you NH4OH plus HF. Now see, as we know, HF have a greater Ka value as compared to Kb, means it is slightly stronger than your base NH4OH. So now what happened? Your NH4 now react with the water and you get NH4OH plus H3O plus. And F minus, which react with the water, you get HF and OH minus ion. So in this case, NH4 ion hydrolyze slightly greater extent, okay, than that of your F minus ion. This means in this reaction there is a more concentration of H3O plus ion as compared to OH minus ion. Okay, in other words, NH4 ion are slightly stronger as an acid than F minus ion as a base. Okay, so in this case, NH4F is thus only slightly acidic and turn your blue litmus into red. Okay, so in this case, NH4 is hydrolyzed at a greater extent than your F minus ion. So that's why in your solution H3O plus ion have a more concentration as compared to your OH minus ion. Okay, and your NH4 plus is slightly stronger acid as compared to F minus as an ion as a base. So that's why your solution become acidic in nature, slightly acidic, and turn your blue litmus into red. Now next we see that is our Ka is equal to Kb. So now what happened? If Ka is equal to Kb, the solution will be neutral. So see the example, that is CH3COO NH4. So it is made up of weak acid, that is acetic acid, and Ka value is 1.8 into 10 raised to minus 5, and weak base, that is NH4OH, whose Kb value is 1.8 into 10 raised to minus 5. So in this case both Ka and Kb are equal. So now what happened? This CH3COO minus plus NH4 plus H2O gives you CH3COOH plus NH4OH. Now in this case, acetate ion react with the water, you get acetic acid and OH minus ion. NH4 plus react with the water, you get NH4OH and H3O plus. So as you know, the Ka and Kb, the relative strength of acid and base produces in a hydrolysis is the same. So therefore the solution is a neutral. And hydrolysis of NH4 plus produce as many H3O plus ion as that acetate ion produce OH minus ion. Means in this case your H3O plus and OH minus ion both concentration are equal. So that's why your solution become neutral. Now next is if our Ka is less than Kb. So now your solution become basic in nature. So what is the example for that? NH4Cl. So in this case the salt is prepared from weak acid, that is HCN, whose Ka value is 4 into 10 raised to minus 10, and weak base, that is NH4OH, whose Kb value is 1.8 into 10 raised to minus 5. So as from the value it is clear that Kb is greater than Ka. Okay, so in this case what happened? NH4 plus Cn minus plus H2O gives you NH4OH and HCN. So NH4 react with H2O, you get NH4OH plus H3O plus. Cn minus react with H2O gives you HCN plus OH minus N. So now in this case what happened? Your Cn can hydrolyze at a greater extent that your NH4 plus ion. Okay, if you see in a reaction that is 19 produces more OH minus ion, okay, then H3O plus ion which is produced in reaction 18. Means in this case your base, that is Cn minus, is slightly stronger, okay, as compared to your acidic NH4, and that's why in this case OH minus will be in a higher concentration as compared to your H3O plus. So that's why your solution will be basic in nature. So in this way, whenever you have a salt of a weak acid and weak base, so you have a three possibility, and that three possibility depending upon the relative strength of your Ka and Kb. If Ka is greater than Kb, your solution will be acidic. If your Kb is greater than Ka, your solution will be basic. And if Ka and Kb are equal, then your solution will be neutral. We start with the next slide, that is buffer solution. Now buffer solution is what? So buffer is what? It is a solution which resists drastic change in a pH when small amount of strong acid or strong base or water is added to it. Means pH is nothing but what? Your concentration of H plus ion. That cannot be easily changed by addition of strong acid, strong base or water in that. So that is the role of buffer solution. So when you take a buffer solution, so that solution has the ability to resist drastic change. Means what? That is a sudden change that can be avoided by using a buffer solution, and that is happening due to the addition of your small amount of strong acid or strong base or water is added to it. So this is very necessary. Means if you take any solution that is not act as a buffer solution, so in that if you add acid or base that is in a strong nature, strong acid or strong base, but in a small quantity, so their pH change may be very drastic in nature. Means as solution originally showing 4 pH, so after addition of strong acid it become 1, so that is nothing but a drastic change. So you have to avoid that change by adding buffer solution in that. So now buffer types, means how many types of buffer which is used. Okay, so there are two types of buffer solution. Acidic buffer used to maintain the acidic pH. So that we see first of all, what is acidic buffer solution? Okay, so now in this case, acidic buffer solution means what? That is a solution containing weak acid and its salt with a strong base. It's called acidic buffer solution. Okay, so solution containing weak acid and its salt with a strong base, that is nothing but your acidic buffer solution. So we take example, that is solution containing weak acid, that is acetic acid. Okay, now its salt with strong base means what? That is sodium acetate. So now both these act as a acidic buffer solution. So now pH of the acidic buffer solution is given by pH is equal to pKa plus log to the base 10 salt upon acid concentration. Now in this case pK is what? pK is nothing but negative log to the base 10 Ka. Now Ka is our dissociation constant of acid. See, for acidic buffer solution we take weak acid and its salt with a strong base. Okay, so weak acid that we taken, that is acetic acid, and salt which we taken, that is sodium acetate. Okay, so in this case what is the pH of our acidic buffer solution? that is nothing but pH is equal to pKa log to the base 10 salt upon acid. Okay, so where pKa is equal to negative log to the base 10 Ka, and Ka is our dissociation constant of a acid. Now next is, our second type is what? Basic buffer solution. So for that we take a weak base and its salt with a strong acid. So what is the example? So weak base means what? NH4OH. And salt means what? That is NH4Cl. That is we taken as a basic buffer solution. Okay. So now in this case, what is pOH of our basic buffer solution? So now whenever we have acidic buffer, we write pH and pK in terms of pKa. But whenever we have a basic buffer solution, so we take pOH and pKb. So pOH is equal to pKb plus log to the base 10 salt upon base. Now in this case, in place of acid we write base. So now as we know, pKb is what? Negative log to the base 10 Kb. Now Kb is what? Dissociation constant of base. Now this equation number 21 and equation number 23 is known as a Henderson-Hazel-Wechsler equation. Okay, so in this way, as we know, buffer solution means what? Which resists the drastic change in pH of a solution, and there are two types of buffer, that is acidic buffer and basic buffer. Acidic buffer we require weak acid and its salt with a strong base, and for basic buffer we require weak base and its salt with a strong acid. Now we see what is exactly happen when you take a buffer solution. So what is the action of your buffer? So first we take, that is our sodium acetate and acetic acid buffer, that is our acidic buffer. Now what happened? Here sodium acetate is a strong electrolyte. Okay, so now in this case it is dissociated completely in a water and producing large concentration of acetate ion as shown below. Now see, what is our strong electrolyte? That is sodium acetate, and dissociated into acetate ion and sodium ion. In this case, your strong electrolyte is dissociated in a water, that is nothing but your sodium acetate, and you get, that is acetate ion and sodium ion. Now in this case, our sodium acetate is a strong electrolyte. It dissociated into your acetate ion and sodium ion. Now on the other hand, we have another compound, that is acetic acid, is a weak acid. So its concentration in undissociated form is usually high. Means acetic acid is in a high concentration. Okay, now in this case, if you add in this buffer solution any strong acid, means what you add? H plus ion. So now what happen? That H plus ion will consume by your conjugated base, that is CH3COO minus, which is present in a large concentration. Now next is what if you add small amount of base, means instead of acid you add base. So now what happen, the added OH minus ion will neutralize by large concentration of acetic acid. Means if you take acidic buffer solution, so what happen, your sodium acetate is a strong electrolyte, so it dissociated into acetate ion and Na plus ion. Now at the same time you have acetic acid, which is a weak acid, weak electrolyte, so it have a large amount of acetic acid that is in a undissociated form. So in that buffer solution, if you add strong acid, so what happen, here H plus ion will be more and that will be consumed by acetate ion. And if you add base in that, so your OH minus ion will be neutralized by your acetic acid, which is in a large concentration. So in this way, your acid or base, can you add anything, but it doesn't change your H plus ion or OH minus ion concentration, and pH of a buffer remain unchanged. Okay, and dilution does not have any effect on pH of a buffer. So in this way, when you take an acidic buffer, they show the action. Now next is properties of your buffer solution. So what is the properties of your buffer solution? So see, if you add small amount either strong acid or strong base, still your pH of the buffer solution does not change appreciably. This is the first, means we can change the pH, but this is the pH of your buffer solution, so it doesn't affected by addition of small amount of either acid or base. Next one is you increase the dilution, still you can't change any pH of your buffer solution. Or if you kept your buffer solution for a long time, still your pH of a buffer solution can't change. Now application of buffer solution. So see first biological application. Now see, as pH of our blood in body is maintained between 7.36 and between 7.42. 7.36 and 7.36 to 7.42. Now this is due to the what? This is due to the carbonate ion and carbonic acid buffer, means acidic buffer only. Now in this case, if there is any change, that is between 0.2 pH, which can cause the death also. So the saline solution used for the intravenous injection must contain a buffer system to maintain the proper pH of your blood. So this is very important. That is, in our body also there is a buffer solution that keep our pH of a blood at a maintained level, that is between 7.36 to 7.42. Now next is use application, that is agriculture. Now see, in agriculture there is a presence of salts such as carbonate, bicarbonate, phosphate, organic acid. Okay, and the choice of fertilizer depend upon the pH of your solution. So that's why when the farmers select the fertilizer for their soil, so they must check the pH of their soil. Then only decided which type of fertilizer is used for that soil. Now next, industry. So in industrial, buffer solution plays a very important role in paper, dye, ink, paint and drug industries. Now next application in medicines. Now see, in penicillin preparations, are stabilized by addition of a sodium citrate as a buffer. So when citric acid is added to the milk of magnesium, so what happened? Magnesium citrate is formed, which is a buffer. Now last application is for analytical chemistry. So in qualitative analysis, a pH of 8 to 10 is required for precipitation of what? Cation third A group. Okay, and it is maintained with the use of NH4OH and NH4Cl buffer solutions. Now next slide is on solubility equilibrium. Now what is the meaning of solubility equilibrium? So see, as suppose some powder sparingly soluble salt such as AgCl. So AgCl is a sparingly soluble salt. We put into water and stir vigorously. A very small amount of AgCl dissolve in a water to form its saturated solution. So most of the salt remain undissolved. So AgCl is a sparingly soluble salt. You put into water and stir vigorously. A very small amount of AgCl dissolve in it and to form its saturated solution. So most of the salt remain undissolved. So in this case, a very small amount can be responsible for its saturation of a solution. Thus, solid AgCl in contact with its saturated solution. So AgCl is a strong electrolyte. Hence, the quantity of AgCl that dissolve in a water, so you get a constituent ion, that is Ag plus and Cl minus. So next is, so there is a dynamic equilibrium between what? Between your undissolved solid AgCl and the dissolved ion, that is Ag plus and Cl minus ion, and it's saturated in the saturated solution. This equilibrium is called solubility equilibrium. So now what happened? There is a dynamic equilibrium which exists between undissolved solid AgCl and the dissolved ion, that is Ag plus and Cl minus, in saturated solution. Okay, so this equilibrium is called solubility equilibrium and is represented by AgCl gives you Ag plus and Cl minus aqueous. So now in this case, what is your equilibrium constant for this? So K is equal to Ag plus into Cl minus upon AgCl. Okay, so in this case, the undissolved AgCl concentration we are taken as K dash. So now we have to put K dash value in equation 24. So what is our next step? That is K is equal to Ag plus into Cl minus upon K dash. Okay, so now next is what? You have to multiply K with K dash, which is equal to Ag plus into Cl minus. So now in this case, K into K dash is what? We use them another constant, that is solubility product, and we write it as Ksp. So now in this case, our Ksp is equal to, that is the solubility product, which is equal to Ag plus into. Okay. Now next is what? For this we are not taking any specific example. We are taking in general example for this. Now general salt, that is what? Bx and Ay, that is in a solid form. So after solubility, means after solubilize, it gives you x times b raised to y plus valency plus y times a raised to x minus valency. Now in this case, what is our solubility product? That is Ksp is equal to b raised to, that is b with its valency, that is y plus raised to x, into a with its valency, that is x minus valency, raised to y. So in this case, this is your equation 26. So according to this, what is our definition for solubility product? So solubility product is what? In the saturated solution of sparingly soluble salt, the product of equilibrium concentration of the constituent ions raised to the power equal to their respective coefficient in a balanced equilibrium expression at a given temperature, it's called solubility product. Okay, these are the definition for the solubility product. So what is solubility product? In a saturated solution of sparingly soluble salt, okay, the product of equilibrium concentration of a constituent ion. So that constituent ion is raised to the power equal to their respective coefficient. Means that power must be their coefficient in a balanced equilibrium expression at a given temperature. It's called solubility product. So we can explain this. Now see some example of solubility product. So as in solubility equilibrium, what is our equation? That is our solubility product is nothing but Ksp is equal to, that is concentration of our cation raised to its coefficient into concentration of anion raised to its coefficient. Now see some example, that is BaSO4. Now BaSO4 dissociate into Ba2 plus and SO4 2 minus. So now in this case our coefficient for barium and sulfate, that is 1. So now solubility product for this is nothing but Ksp is equal to concentration of barium cation in +2 oxidation state, which is raised to 1, into sulfate in 2 minus oxidation state raised to 1. Now take another example, that is CaF2. Now CaF2 will give you Ca2 plus and 2 fluoride ion. Now in this case our coefficient for calcium is 1 and fluoride it is 2. So now Ksp is equal to what? Concentration of calcium 2 plus raised to 1 into concentration of fluoride minus ion, which is raised to 2. Now third example is what? Bismuth sulfide, that is Bi2S3, which gives you 2 barium in 3 plus oxidation state plus 3 times S2 minus. Now solubility product for this is equal to barium, which is in +3 oxidation state raised to 2, into sulfide, which is in 2 minus oxidation state raised to 3. Now fourth example is calcium phosphate. Now calcium phosphate is dissociate as 3 times Ca2 plus and 2 times PO4 3 minus. Now solubility product for calcium phosphate is what? That is concentration of Ca2 plus raised to 3 into concentration of PO4 3 minus raised to 2. Now see the solubility product as our definition, that is, when you take a saturated solution of sparingly soluble salt, the product of equilibrium concentration of constituent ion raised to power equal to their respective coefficient in balance equilibrium expression at a given temperature. So this is nothing but your solubility product, and these are some examples that explaining how you apply solubility product for this sparingly soluble salt in their saturated solution. Now, thank you for continuing in the next lecture.